So I'm going to present some really easy to comprehend groups, uh, which will hopefully like make group theory feel easier to you. So first, let's just think about the group of integers, right? Represented as z. So it's like every single integer, and the operation that we're going to do is addition in this. So for every element x in integers, you clearly have an inverse, you have an identity in z, obviously. So 0 is the identity element for addition over integers. For every x in z, you have its inverse minus x in z, right? uh, yeah. And so that already you know follows two sort of requirements for a group. You also have associativity, so that's another requirement, and you have closure. So for any a and b in z, a plus b is also an integer, like obviously. Yes. So yeah. uh, so the set of integers with the operation addition is the group z. So yeah, I mean, it's the additive group over all of integers. Cool. um okay, so this was a bit too simple. Let's think about a slightly more, slightly better example. Let's think about, once again, just just the integers, but like only the first n natural numbers essentially. And the operation is now addition modulo n, right? So this is basically the residue classes. It's the first n whole numbers, I should say, not natural numbers. So this set is like what? It's just 0, 1, 2 all the way till n minus 1, right? And addition modulo n, what that means is that you have any a b in this set, you do the group operation as you just add them, and then you take a mod n, right? So you find the remainder of a plus b with respect to n, and that's what a plus n b is, right? So this is also a group. So notice that since it's mod n, so a plus b mod n, that's obviously going to be less than n. Like remainders are strictly less than n, like the divisor, obviously. So what that means is that a plus n b is in this set, right? So it's in Zn if a and b are obviously in Zn. Even if they're not, if they're just in Z, it's still going to be in there. But yeah, so closure is there. Is there an identity? Yes, 0 is still an identity, right? Because 0 plus nb is just 0 plus b mod n, which is like b mod n, but that's just b because b is already in the list of remainders, possible remainders upon division with n, right? And so 0 plus nb is just b, right? So there's closure, right? This is closure. This is the existence of an identity. Is there also the existence of an inverse for every single element? So yeah, there is. So for 0, the inverse would just be itself, right? So 0 inverse is 0. For 1, it would be uh, n minus 1. So like figure it out. You can figure out the pattern, right? So like for x inverse, that's just n minus x, right? So you add x and n minus n, sorry, and n minus x modulo n, right? And you get just 0. That's what I'm saying. And so n minus x is the inverse, and this goes both ways. So this is a commutative group, also called an abelian group, right? Every group where the operation is commutative, it's called an abelian group. The spelling is weird. I still don't know why they use this word rather than just commutative, but well, I guess you just gotta stick with the notation sometimes. Okay, so that's this group Zn with addition modulo n, obviously. A nice property is that Z sub n is generated completely using, so okay, I shouldn't go into generators right now, but what you can essentially say is that every element just can be thought of as 0 plus 1, and then 0 plus 1 plus 1, 0 plus 1 plus 1 plus 1, and so on, right? And so this is generated, and it should be plus n actually, and just keep going, and you just still get this because it's like starts to loop around, and then just set, so there can only be one instance of every element. And so we write it like this: it's generated by 1. Yeah. 0 is the identity, so we don't write that there, but like obviously with identity 0 and the element 1 and the operation, you can generate this thing. Okay, so that's Zn. Let's go to this group called the group of units modulo n. So this is slightly different. Okay, it's not, it's addition. Addition is not what it is, it's multiplication now. So addition was straightforward, but what about multiplication? So if you just consider Zn and then multiplication, this is not a group, because you know what are you going to multiply with 0, like such that this becomes the identity, which is 1. Like, can this even happen? And the answer is no. 0 times anything is just 0, so this can never be equal to 1. So clearly Zn with the multiplication modulo n, that is not a group. But something else which is a subset of Zn is in fact going to give us a group. So Un is basically like, it's everything in Zn such that the GCD of x and n, that's 1. That is to say, x and n are co-prime. So it's the set of all numbers co-prime to n before n, right? So for example, u sub 6, that would be like 1, because GCD of 6 and 1 is obviously just that. 0 is not there, notice that, because the GCD would be 6 obviously. So 1, 2 is not there, 3 is not there, 4 is not there, 5 is there, and that's pretty much it actually. So u6 is just that, and then obviously you gotta have u6 with multiplication modulo 6, and that's the group, right? And you can notice that you make the Cayley table of this thing. Notice that 1 times 1 is 1, 1 times 5 is 5, 1 times 5 is 5, 5 times 5 is 25, but not anymore, because 25 is 24 plus 1, so it's just 1 actually. And so for every element you have the inverse, right? Because the identity appears in every column. The inverse exists, like so 2 things down. There's closure, obviously, because no extra weird element appears, only 1 and 5 appear. So there's closure. And then there's associativity, because multiplication. So even if it's modulo n, it's still just multiplication essentially. So yeah. And you know the way it works, right? Like if you have even a slight bit of intuition, I think you can do it yourself. You can prove that yes, it's associative. Okay, so this is called the group of units, and this is like very important in number theory, because like some things come out of it, like if you use this, but well, never mind all that. We just want to give examples right now. So the group of units, that's there. Yeah, okay, we can think of the quaternion group, but okay, but that's probably a bit too long to express right now. You obviously have the very first example that you had, the set 1 iota minus iota and minus 1, right, with multiplication. That's like the complex numbers, right? It's like the basis for all complex numbers essentially. Yes. Then you also have the quaternions, so it's 1. Okay, this one is going to be big, so it's iota j k minus I minus j minus k, and the way these like way these interact is that I times j is so and for any like I j k, I square is just minus 1, j square is minus 1, k square is like minus 1. Okay, you obviously have to have minus 1 over there as well too, right? And then I times j is k, j times k is I, k times I is j, but then j times I is minus k, then k times j is minus I, and then I times k is minus j. So this is the quaternion group, obviously multiplication, that's the group operation. Yes, cool. So these are some very simple examples of groups, and obviously you have things like S sub n, which is the symmetric group of n elements. And yeah, I think these are, and like dihedral group, that's another example. So I think like that's good enough for now. Like these are some good examples. So I'll see you guys in the next video.